All right, so this is kinematics, which I'm calling kinematics part 2, building on top of what we did with the last lesson, but this is going to be with and without integration. So we've got our first question 1 is going to be without integration. So we've got a graph, and it's a straight line graph, and that should tell you a few things. So let's have a look at that first. So first of all, let's read the question. We've got a diagram showing a velocity time graph, and it's for the motion of a machine cutting tool. So this could be like a, an engraving machine or a laser cutting tool, or one of those like 3D printers. And the graph consists of 5 straight line segments. The tool moves forward for 8 seconds while cutting, and then takes 3 seconds to return to its starting position. Find the acceleration of the tool during the first 2 seconds of motion. So first of all, let's just look at the graph. This is a velocity time graph. So it's very important that we understand that what this is showing isn't the displacement of the tool. It's not the tool moving up and moving down. It doesn't show that. It shows the velocity over time. So it's, how fast is that tool piece moving? And the fact that it's all in straight lines tells you that the acceleration is constant for each individual segment. So we don't have to use integration to find the area. We can use areas of triangles and areas of trapeziums. So it's super important that you know how to find areas of triangles and trapeziums. But that's GCSE maths, so I kind of assume that you all know it. Yeah, so make sure you understand, if you see a velocity time graph, you might look at it and just think, oh, it's showing it going up and down. It's not showing that. It's showing the velocity. So the velocity, when it's positive, it is moving up, but it doesn't show necessarily the distance it's moved up or the displacement. Okay. Whiteboard Fox keeps doing this. I think they must have a problem with the server. Let's see. So if we have a look, we've got our first segment. So there must be a positive acceleration there, because my velocity's changed. It's gone from 0 to 0.18. So my velocity is increased. So there's been a positive acceleration. So I guess maybe I can write that on. Positive acceleration for that first segment. Then when my velocity stays the same, there can't be any acceleration. So acceleration is 0. Then we must have a negative acceleration or a deceleration because my velocity is decreasing. And then we have a negative acceleration, and then finally a positive acceleration. Okay, so part 1, find the acceleration of the tool during the first 2 seconds of motion. Well, acceleration is the rate of change of the velocity over time, dv dt, right? But I've said we're not using calculus, we're not using integration or differentiation. So actually what this is the slope of this line. So we want to find the slope of this line. That will be our acceleration. Okay. dv dt is the slope of a function, a general function, if it's a straight line, or if it's not a straight line, dv dt or dx dv dx, whatever it is, will give you the slope function. So it's the slope of the line. That's what we need to find. So, I mean, this is very, very kind of simple GCSE maths, but it's rise over run, or delta y over delta x. Okay. So this is even easier than the integration or calculus type questions. Acceleration for the first 2 seconds will be the change in height, 0.18 divided by 2, which would be 0.09. And the velocity is in meters per second and the time's in seconds. So my acceleration will be in meters per second squared. Easy, 1 mark, easy. So that's part 1. Let's go to part 2. So part 2, find the distance the tool moves forwards while cutting. Okay, so we need to think, which part of the graph is the tool moving forwards? Well, if my velocity is positive, you could imagine if this was describing like a car driving, then if the velocity is positive, you're moving forwards. If the velocity is negative, you're moving backwards. So actually, I need to find the distance it's traveled in the first 8 seconds, because that's all got a positive velocity. The tool will be moving forwards throughout that whole time. Okay, so from 0 to 8, I need to calculate how far it's moved. And the distance is the integral of velocity over time. So this is equivalent to the area under the graph or the curve, right? Again, we're not using calculus, but the same principles hold true. And if I told you what these functions were in terms of a straight line function, I could describe those lines as functions. You could integrate those functions and you would get the right answer. But we don't need to do that. We just need to find the area under this shape, and it's a trapezium, right? You could break it down, of course, into triangle, rectangle, and another triangle. It turns out the area of the first triangle has to be equal to the area of the second triangle, because the base of them is the same and the height of them is the same. So there's different ways to do this question. You could do it triangle, rectangle, triangle, and that would be fine. I'm going to do it using the area of a trapezium. So the area of a trapezium is a half times the parallel sides added together. So we've got 8 plus, and the other parallel side is this one along the top here, which has a length of 4 times the height. So that's a formula you need to memorize, right? Half the sum of the parallel sides times the height between them. That's the way you calculate the area of a trapezium. So we've got 8 plus 4 is 12. Half of 12 is 6. So we've got 6 times 0.18. And I'm just going to use my calculator to work that out, because my brain's not working this morning. So we've got 6 times 0.18, 1.08. And the units will be meters, because the velocity is given in meters per second, and we've multiplied that by seconds, so we get meters. Okay, easy 3 marks. Part 3. Let's use black. Okay, so what do we ask for here? The greatest speed of the tool during the return to its starting position. So it's not asking for velocity here, it's asking for speed, the greatest speed. So whether the velocity is positive or negative doesn't make a difference for speed. Speed doesn't care which direction you're going, it just cares how many meters you're going in how many seconds it takes you to go that many meters, right? The rate. So this is going to be the well, this is going to be where the height of the graph is either at its highest point or at its lowest point. If we think about what the graph is, it's velocity going up the side, right? So at the start, it has 0 velocity. So that's obviously not going to be the greatest speed if it's not got any velocity. and then it increases to a maximum of 0.18. So that's that would be the maximum speed for the first 8 seconds of the journey would be 0.18. And then in the second part of the journey, between 8 and 11 seconds, at 8 seconds it has a speed of 0, and at 11 seconds it has a speed of 0. But then kind of halfway in between, looks like halfway in between those two, it has its maximum speed. So that's going to be actually the height of this triangle. So this is going to be I'm going to call it the magnitude of Vmax, right? The maximum speed. So what we need to find is the height of that triangle. During the return to its starting position, so it's during that part. So what we need to know in order to work out the height, if you think about things that we could possibly know about this triangle, well, we know the base, right? We know the base of the triangle is 3. The height is what we're trying to work out. The height is not given. We don't know what the height is. So the only other thing about the triangle that we could possibly know would be the area. So how could I possibly know what the area of this triangle has to be? Well, I just worked out the area of the trapezium in part 2. So if the tool has gone a total distance forwards of 1.08 meters, right, then it must be going, when it's going backwards, and for all of that triangle it's going backwards, even though the slope goes up, it's acceleration. The slope is acceleration, not velocity. Velocity is always negative. So it's always going backwards for that triangle. So the area of that triangle must be the same as the area of that trapezium that we just worked out. And that's the logic there that you have to kind of think through in your head. That's the hard bit of this question. So the area of the triangle is equal to the area of the trapezium. Okay, again, that just comes from understanding what velocity time graphs are and what they actually say, and not confusing velocity time graphs with displacement time graphs or acceleration time graphs. Okay, so that means that the area of the triangle is 1.08 meters. And we know that the formula for the area of the triangle is 1/2 times the base, which we said was 3, times the height, which I called magnitude of Vmax, must be equal to 1.08. Now it's just easy, right? It's easy to solve. So we've got 2.16 divided by 3, the maximum speed. And I'm just going to use my calculator again because I can't do that in my head. .72. Okay. So I think that's pretty easy. Does anybody have any questions? I'm going to unmute you guys for a sec. Any questions or anything on that you're not sure of?
No.
Is that all right?
No.
Great. Okay, so let's have a look at one with integration with calculus now. So this would be a harder one. This is question 2. Sorry for the poor quality of the image. It's just, I think it must be taken from a paper that was quite a while ago, but that's the highest quality I could get. I'll just have to deal with it. I'll read it out. So we've got a man who's walking in a straight line from A to B with a constant acceleration. So let's draw a diagram. Let's say we're going from A to B. So we'll put A here and we'll put B here. So the man's walking from A to B. with a constant acceleration of 0.004. So that means that his speed is increasing as he goes. So his speed at A is 1.8. So V of A is 1.8. And his speed at B is 2.2. Okay, so it's really important to draw a diagram, even for a situation like this where you think it's just simple, it doesn't give you any diagram in the question, draw one. So he starts with that speed, he finishes with that speed, that's his acceleration, and it's constant. So that's quite nice. It's not changing, it doesn't depend on time. Find how long it takes for him to walk from A to B, and find how far that distance is from A to B. So we need time from A to B, and we need the distance from A to B. So write those down as well, because it's very easy to forget once you've finished finding the time. Oh, I was also supposed to find the distance. So I just write down what I'm supposed to find, and that way I won't forget it. Okay, so there's probably a few different ways we could do this, but if we've got constant acceleration, then actually we don't really need to use integration. We could use suvat. So this really is a suvat question. So I'm asked to find the time and the distance. So those are two variables I don't know. So I have all of the other three. I know initial velocity is 1.8, final velocity is 2.2, acceleration 0.004. So this is easy as well, right? This is a really easy question. What are we going to find first? Let's find t first. V is u plus at. Rearrange it to make t the subject before you plug the numbers in. T is v minus u divided by a. Double check you've got that correct, because if you make a mistake there, you'll get everything else wrong. So the difference between the velocities divided by the acceleration. So we've got 2.2 minus 1.8 will give us 0.4. And we're dividing that by 0.004. So this is the same thing as what, 4t 400 divided by 4 times by 10 times by 10 again would be 40, 400. Yeah, is 100. Yeah, just doing it in my head. I just wanted to make sure I get it right. So yeah, 100, and this is time, 100 seconds. Great. Working out displacement, or S, should be pretty straightforward. S is ut plus a half at squared. Would be probably the easiest one because it's already in terms of S. I think there's another one, right? If we got S equals a half U plus VT, that could work as well. So what have we got? UT is 100 times 1.8. So that's going to be 180 plus a half of A, 0.002 times 100 squared is 10,000, 100. So this should give us, gonna guess it's about 200 meters, but could be wrong. 180 plus 0.002 times 10,000. 200, bang on. Okay, easy. Okay. Part 2. A woman cyclist leaves A at the same instant as the man, and she starts from rest So she's starting with initial velocity 0, and she travels in a straight line to B, reaching B at the same instant as the man. So that tells me that she reaches B after 100 seconds, because I just worked that out, right? So separate diagram. You could try and put them on the same diagram, but I'm just going to do a separate one. This one's for the woman. So she's also going from A to B. She starts with a velocity of 0, and it takes her 100 seconds. This is t equals 0 to get there. So just putting the information down on the diagram. At time t, after leaving, her speed is given by this weird function k times 200t minus t squared, where k is a constant. So what's it say? Her speed. So I'm going to call this v of t, is given by k, and it was 200t minus t squared. 200t minus t squared. Okay, great. Find the value of k for part A. So this is part 2A. Find k. Okay, what else do we know? Well, I also worked out the distance is 200 meters. So let's put that on there as well. All right. So her velocity is given by this weird function here. So her velocity depends on time, and it's got a t squared in it. So that tells me that her acceleration is not constant. Think about what acceleration is. It's dv dt. If I differentiate this velocity function, it's still going to depend on time, right? The first t will drop out, but the t squared term will go to 2t. So the acceleration depends on time. So I can't use SUVAT anymore. It should be kind of clear anyway, but this is going to have to involve integration, differentiation, and calculus. So there's two ways I could go here, really. I could try and differentiate v of t, which would give me acceleration, a of t. Or I could try and integrate v of t, which will give me s of t, which would be displacement. And I know what s of t should be at t equals 100, because I know it's 200 meters. So I know that one. I don't know the acceleration, right? I don't know. I don't know anything about acceleration. So I'm going to go with the integral, right? I'm going to go and integrate. So I'm going to say, well, s of t is the integral of v of t. And if I integrate from 0 to 100, I know that that should be equal to 200 meters. So integrating the velocity function from 0 to 100 seconds gives me the total distance traveled, which I know is 200 meters. Okay. So that then hopefully will help me to work out k. So I guess I want to try and sketch this function first, because I've got a sneaking suspicion that it won't be as easy as that. So let's just expand out this bracket. We've got 200 kt minus kt squared. If it's a minus, that's going to be a parabola, an inverted parabola. So I'm going to sketch the function before I do anything else. And I don't always recommend doing that. You guys should know from integrations in core that integration gives you the signed area under a graph. So that's where the difference between displacement and total distance traveled comes from. Your displacement could be 0 because you've just run in a circle, but your distance traveled could be 200 meters. Okay. So think about how we could sketch this function. Essentially, what we've got is like a minus at squared plus a of t, or plus b of t. So it'll be a quadratic. It's probably doing something along these lines. Okay. At t equals 0, it has to be 0, so that's wrong. T equals 0, we've got a root. Do we have another root? Yeah. If I factor out a t, and I factor out the k, kt, we can say this is 200 minus t. So either k times t equals 0, and k is not 0, so t is 0 is the solution, or t is 200 is the other solution. So my parabola will be doing something like that. Oops. Something like that, which means I'm actually only interested in this area here from 0 to 200. So I don't need to worry about the signed area. But it's important to think of that, because this is Cambridge. They make questions ridiculously hard, and it's possible that that might happen, especially if it's question 6 on a paper, you know. They love to do stuff like that. So I don't need to worry about the sign of the area. When I do this integral, I can just carry out the integral without breaking it into segments. Okay, so let's do it. We've got the integral from 0 to 100, and now I can plug in 200 kt minus kt squared dt, and this is equal to 200. Sorry, this would be t is 200 is the solution. It's actually 100 is when is the area I'm finding. Sorry about that. So I'm actually only finding the area up until here. Okay. But the distance traveled is 200. Is that correct? Yeah. Okay. So let's integrate. We raise 1 to the power, divide by power, so this becomes 100 kt. This is called the privative. So we're finding the privative now. This is 100 kt minus kt cubed over 3. Evaluated from 100 to 0. Well, when I plug in 0, I'm going to get 0. So I really just need to evaluate this at 100. So this is going to be 100 cubed times k minus 100 cubed over 3 times k. So I can kind of clean this up a bit, factor out the k. 100 cubed minus 1/3 of 100 cubed is 2/3 of 100 cubed. And now I can just solve it for k and say, well, k must be equal to 200 divided by, put the 3 up there, put the 2 down here. Cubed is 100, 100, 100. And just plug that into a calculator and find k. Okay, so what we got? 600 divided by, that's 2 million, isn't it? 2 million. 0.0003, which is 3 over 10,000. Okay. So we found k, and then that was quite a lot of work to find k, but it was 4 marks. And then find the cyclist speed at b. So we need to find v of b. Okay, this is B, part 2B. V of B. So this is the velocity when the time is equal to 100. And now I know what my velocity function is because I know what K is. And this is V in terms of K. I can now just plug in K to get like an exact function for V. So V of T is equal to K, which is 0.0003 times T 200 T minus T squared. Okay. So V of 100, I just have to substitute in 100. And you can just crunch that in your calculator. I do recommend maybe writing out an additional step because you don't know, you get a mark for accuracy mark for the final answer, but you don't know how many marks there are for method or for stating things. So just stating that that's what you're doing, that I'm substituting in 100 for T and actually writing that down, even though you can kind of do this in your head, it just means if you did type something wrong into your calculator, you could still pick up a mark. Okay, so actually do the substitution and actually write it down. And then once you've written it down, then you can calculate. And that way, if I did make a mistake, I would still be getting all of the marks except for the accuracy mark. So we've got 200, 100 minus 100, 100, which is equal to 3 meters per second. That's a nice value to get. When you get a 3, like a whole answer like that, kind of makes you feel like you've probably got the right answer. If I got like a 3.275, blah, 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 I'd be thinking, I may have done something wrong. Okay, great. So this now was equal to 3. How long do we have? We've not got very long. Sketch using the same axes. Well, I haven't got any axes here. The velocity time graphs for the man's motion. Oh, okay. And the woman's motion from A to B. Okay. I kind of have a sketch down here that I can kind of look at. So the man's motion, he had a constant acceleration of 0.004. Her final speed was 3. So this is V of T. The woman's is in black. Let's do the man's in red. And what was the man's final velocity? It was 2.2. So if that's 3, I'm going to say 2.2 somewhere around about here. I'm doing this very kind of quickly because we don't have much time, but it would look something like that. Yeah. Any questions? Gonna unmute you. Any questions?
Not really.
No?
I don't think so.
All right. I thought that was okay, really. I mean, there are some harder questions than that, but it's just that kind of decision making at each stage. Think it through. Like, what happens if I differentiate? What do I find? What happens if I integrate? What does that tell me? What information do I have? And it's that problem solving. That's what Cambridge loved. They love that problem solving mathematics where you really thinking through a problem and you have it's not just about being good at maths. It's about being good at kind of like interpreting maths and being able to think steps ahead. So yeah, there you go. I'll make this board available for you guys on the Google Classroom, and I will also upload this video to YouTube so you can watch it back if you need to, and hopefully this will help you to answer tomorrow's assignment, which is already available. Okay. Stop recording.